Assalamualaikum and hi students. So this is a lecture video for BMCG 1013 differential equations. So we are still in chapter 1, first order linear differential equations. In the second part of the chapter, we will discuss on how to solve the first order ODE using numerical methods. So the learning outcomes that will be covered in this lecture video is these two LOs, which are to solve the first order ODE using Euler's method and Ralston second order Rungke-Kutta method. Subtopic 1.3 Numerical methods, Euler's method second order Rungke-Kutta methods. So in numerical methods, it is a numerical process for generating a table of approximate value of the function that solve the initial value problem. So using numerical method, we will just get an approximate value, not the exact value, as given by the analytical method we discussed before in the previous video. Okay, and for numerical methods, we will just solve the initial value problem. However, by decreasing the step size and therefore increasing the number of iteration. So when we reduce the step size, we will indirectly increase the number of iterations. So it will give a better approximation to the exact solution. Okay. Euler method is the most basic explicit method for solving ordinary differential equation. So this is the general solution for Euler method. We will use this formula. Yn is equal to yn minus 1 plus hfx n minus 1 yn minus 1. N is the number of iteration. Okay. And h is the step size. I will show you how to solve the first order ODE using Euler's method in example 1.7. So first example, in example 1.7, use Euler's method to integrate numerically dy over dx equal to x cubed minus 2x plus 3. So remember, the general form for first order ODE, we have dy over dx equal to fx. So this is your fx. Okay, and then we have to do from x equal to 0 to x equal to 3 with a step size of h equal to 0.5. And given the initial condition at x equal to 0 is y equal to 1. So for Euler's method, you need to have these three columns, a table with these three columns. The first column is n, the number of iteration. We start with iteration 0. Okay. And then you need to have your x. So xn is basically equal to xn minus 1 plus h, the step size. And this is the formula for Euler's method. Okay, yn equal to this term. Okay, first we start with n equal to 0. So for n equal to 0, use your initial condition given. So when x equal to 0, so x0, number of iteration 0 is equal to 0. Then you have y equal to 1. So y0 is equal to y0 is equal to 1. Okay, that's it. Okay, just substitute the initial condition. For the first iteration, moving to the first iteration, we have x1 equal to 1. N is 1. Sorry, x1 equal to the previous x plus h. So 0 plus 0.5, since our h is 0.5. So we have x1 equal to 0.5. And then for y1, so y1 is equal to, your n is equal to 1. So y1 minus 1 is y0 plus h, your step size. Substitute your step size, which is 0.5. And then you have the function of x n minus 1, y n minus 1. So this is x0, y0. And then substitute what is your x0 and y0. So x0 and y0 is 0 and 1. So this is 1 plus 0.5 f01. So how do you find your f01? Okay, so for this one, you need to substitute the value of x equal to 0 and y equal to 1 into this fxy. Sorry, this is not fx, this is fxy. Okay, so for this one, you have 1 plus 0.5. So f01 is equal to, you substitute your x equal to 0 cube minus 2 multiplied by 0 plus 3. Okay, so for this one you have 2.5. Okay, you don't substitute the y because you don't have any y in this fxy. That's why you don't use the 1 here. Okay, let's repeat with the next iteration. So move to x2. So now you have your x2. x2 is equal to your x1, the previous x, plus with h. So you have 0.5 plus h 0.5, so you have 1.0. So for x equal to 1.0, you have your y2 equal to, okay, the previous y, which is y1 plus h 0.5 f previous x and previous y, x1, y1. And this is equal to y1 equal to 2.5 plus 0.5 f, okay, 0.5 and 2.5. Okay, again substitute the value for x and y, the previous x and the previous y. So you have 0.5 multiplied by 0.5 cube minus 2 multiplied by 0.5 plus 3. And this gives you the answer of 3.562. Let's try with x3. For x3, your x is 1.5 now, and your y3 is equal to y2 plus 0.5 f x2 y2. And this is equal to 3.5625 plus 0.5 f 1.0 and 3.5625 for y. And now you have y3 equal to 4.562. Okay, so you need to find the value for y when x equal to 0 until x equal to 3. So you need to continue your iteration until. So if you have x4 is 2.0, and then x5 is 2.5, and the sixth iteration x6 is equal to 3.0. So you need to stop here. Okay, you can proceed with the rest of calculation. Okay, once you are done with your calculations, you can check with my answer. So for y0 we have 1, y1 is equal to 2.5, y2 is equal to 3.5625, y3 is equal to 4.5625, y4 equal to 6.25, y5 is equal to 9.75, and y6 is equal to 16.5625. For the second example of example 1.7, you need to repeat the calculation by using h equal to 0.1. For example above, okay. Find y3 at x3 equal to 0.3. Okay. So before this, your h is equal to 0.5, but now the question reduce the size of the step size. So the value for the step size. So what will happen to your answer? Okay, so start with n equal to 0. So substitute your initial value. X0 is equal to 0 and Y0 is equal to 1. Okay. Then for X1 now becomes 0.1. Okay, since your H is 0.1, so 0 plus 0.1 is 0.1. Okay, for Y1 is equal to Y0 plus H is 0.1 F Xn minus 1 is X0 Y0. Okay, for this you have 1 plus 0.1 F0 1. Substitute the value for X and 1, X and Y, which is 0 and 1 in 0 and 1 into the same Fxy, which is X cubed minus 2X plus 3. So you have 1 plus 0.1 multiplied by 0 cubed minus 2 multiplied by 0 plus 3. And the last answer is 1.3 for X1. So X1 is equal to 1.3. And then continue with X2, 0.2. You will have your Y2 equal to Y1 plus 0.1 Fx1 Y1. Okay, so for this one, substitute Y1. Y1 is 1.3 plus 0.1 F0.1 1.3. And the last answer is 1.5801. Then find what is X3 equal to 0.3. Okay, find what is the next value for X. X equal to 0.3. Okay, for X3 equal to 0.3, you are supposed to get Y equal to 1.8409. The second method is called Ralston's second order Rungke-Kutta Method. So basically, what is Rungke-Kutta Method? It is a method of numerically integrating ODE, first order ODE, by using a trial step at the midpoint of an interval to cancel out lower order error terms. Okay, there are various types of Rungke-Kutta methods that can be devised by employing different numbers of terms in the increment function. But in this syllabus, we just consider the second order Rungke-Kutta method. So that's why we just have two terms in the increment function. So we have K1 and K2 for Ralston's second order Rungke-Kutta method. Okay, if you have a fourth order Rungke-Kutta method, so you will have 4K, K1, K2, K3 and K4. So this is the formula for Ralston's second order Rungke-Kutta method. Yn is equal to Yn minus 1 plus 1 over K, 1 over 3 K1 plus 2 over 3 K2 H. From here, you need to know what is your K1 and K2. So, to find the K1, K1 is equal to the function of your previous X and Y. Okay. And then K2 is a function of your previous X and Y with additional K 3 over 4H for X and 3 over 4 K1H for Y. We will try to solve the initial value problem for first order ODE using Ralston's second order in this example 1.8. Okay. Use this Ralston's second order Rungke-Kutta method to solve the following initial value problem. So you have Y prime minus X minus Y equal to 0. So this is basically Y prime equal to X plus Y. And X plus Y over here is our Fxy. Okay, so this is our fxy. And the initial condition is y0 equal to 1. Okay, this means when your x is equal to 0, your y is equal to 1. Okay, using step size h equal to 0.25 for 0.25 x. This is the value for x until 0.5. They give you the interval of x from 0 to 5 to 0.5. So for this, you need to construct a table, okay, with 5 columns. First, you need to have your n column, the iteration, then xn as usual, then you have k1, k2 and yn column. So this is yn minus 1. Okay, start your iteration with n0. So we have xn equal to 0 from our question, And for first iteration, we don't have any k1 and k2 yet. Okay, just moving to yn. So yn, y0 is equal to 1. x0, y is equal to 1. Okay, and then for x equal to 1, the first iteration, x equal to 1, is equal to 0 plus your step size 0.25. So we have x equal to 0.25. Okay, and then for k1, you know that k1 is equal to f, your previous x naught and y naught. So f0 and 1. For f0 and 1, refer to fxy. Your fxy is x plus y, meaning that you have 0 plus 1, and your k1 is 1. Okay, and then for k2 is equal to, okay, function of x, previous x naught plus 3 over 4 h. Our h is 0.25. Okay, and then y, for y, previous y, plus 3 over 4 k1. K1 is 1. Then h is 0.25. Then substitute the value of x naught and y naught. Again, x naught is 0. And y naught is equal to 1. So you have here f 0.1875, and over here you have 1.1875. Okay, so substitute into your fxy. You have k2 equal to 1.375. Okay, and last, you need to find what is your yn. y1, use k1 and k2. Okay, k1 and k2, we have y1 equal to previous y, which is y0 plus 1 over 3, k1 is 1, plus 2 over 3, k2 is 1.375, multiplied by 0.25. Okay, so y0 is 1 plus, need to substitute this value, and your last answer, I will just give you the last answer. This is 1.3125. Okay, once you have your x1 and y1, you can proceed with the last iteration, which is x2 equal to 0 to 5, because you need to find this value. Y for this x value 0.25 and 0.5. Okay, so find k1 for this is fx2 1 y1, and you will get 1.5625. Okay, try to do this yourself. In K2, you have f x1 plus 3 over 4, 0.25, y1 plus 3 over 4, substitute K1, 1.5625, multiply by your h, okay, 0.25. For K2, you have 2.043. And last, for y2, it is equal to 1.7832. Okay, you just need to know how to substitute the value using your calculator, and do not make any careless mistake. Okay, and then you are fine. This is the last example for this lecture video. So you need to continue the calculation by using h equal to 0.2.5, the same step size as before to solve the example before. Okay, but you need to find your y3 at x3 equal to 0.75. So what you need to do is just proceed with the next iteration. So you can try this. Then this is the last answer. So this is x3 0.75. You will have your K1 equal to 2.2832. Your K2 value is equal to 2.8988, and your y3 value is equal to 2.4566. Okay, that's all for this week video. For the next video, we will start a new chapter, chapter 2, on second order ordinary differential equations. Thank you.